Hello friends, welcome to all of you. In today's lecture, we are going to talk about five concepts. This is the lecture number 2 of electrochemistry I have mentioned here. So the first which we are going to learn in today's lecture is the factors affecting electrolytic conductance. After that, Caldes Law, application of Caldes Law, construction of cell, and then cell representation. All the concepts are very much important here in this particular lecture. So I will try to explain in a simple language. So the first thing which we are going to learn in today's lecture is the factors affecting electrolytic conduction. Electrolytic conductance. Now see, when you do electrolysis that we are going to learn in the coming lecture also, so the ion starts moving. So you have given the heat. You have given the heat. What I mean to say the heat, the first factor that can increase the conductivity can be the temperature. Can be the temperature. Now see, when you heat any electrolytic solution, so what happens? The ions get a kinetic energy. How they get a kinetic energy? Because of a heat. So as the temperature as the temperature of electrolytic solution electrolytic solution increases, so what is going to happen? The conduction is also going to increase. The conductance will also increase. Why it is going to happen? Because the kinetic energy is going to increase. So what is going to do this kinetic energy? The kinetic energy of the ions increases, and whatever the amount of attraction is present between the ions, that is going to get decreased because the kinetic energy is increasing, so they start randomly moving. So the temperature plays a very important role for increasing the conductance of an ions. After that, the second factor which can decide the conductance is the interionic attraction. Interionic attraction. See, if the attraction is very high, so we can say that they are not going to move. So conductance is not going to happen in so rapid way. So what I can say about the interionic attraction, if the interionic, if attraction between the two ions, the attraction between the two ions is called as a interionic. This is the positive and the negative. If the interionic attraction between ions is more, so the conductance will be less. That is very much understandable that if the two opposite ions are pulling each other, so they are not in the position to move. So what we are supposed to do? We are supposed to just heat it. So when you are heating, the attraction is gradually decreasing. If the interionic attraction between the ion is more, the conductance will be less. Will be less. So this is the second point. After that, the polarity of the solvent, because where you are going to add the solute, polarity of solvent, that is also very important. If the solvent is having a very high dielectric constant, then the ionization and the conductance both will happen. Unless there is a no ionization, it means there is a no ion formation. So solvent should have a very high dielectric constant where you're going to put an electrolyte or your solute. If solvent has high dielectric constant, then ionization and the conductance, ionization and conductance, both will be high. So this is the third factor. After that, you can have a viscosity of the medium and the dilution. So there are two more factors which can affect the electrolytic conductance. Now see, there is a viscosity. Now the viscosity of medium. Now, as the viscosity of the medium is increasing, the conductance is going decrease because the freedom of the ions are getting less and less. They are very much concentrated at one particular point. So I can say that on increasing the viscosity of medium, the conductance the conductance decreases. So this was the fourth factor. Now the next factor is the dilution. Is the dilution. Now, as you know that there are strong electrolyte and the weak electrolyte. When you are putting a water inside the strong electrolyte, the dissociation is getting increase and increase and increase. So the interionic force of attraction is getting decrease and decrease. So what I can say that for on increasing the dilution, conductance, that is your G, increases because the attraction between the ions keeps on decreasing. Okay, so this is the your explanation. For strong electrolyte, your for strong electrolyte, as the dilution is happening, as the dilution is happening, the force of attraction decreases. The force of attraction decreases. Okay, therefore the conductance increases. Therefore the conductance increases. Now, when you talk about the weak electrolyte, for the weak electrolyte also the dissociation increases, therefore the conductance increases. So for both, whether it is a strong electrolyte or the weak electrolyte, the conductance are increasing. So these are the five factors which play a very important role for deciding the conductance. Now, moving ahead, the next concept was the Kohlrausch law. So we see the Kohlrausch law and its application. See the what is the Kohlrausch law? The law states that, first we'll understand, then I will write it. Now the Kohlrausch law. If you have any electrolyte and you are putting a lot of water at infinite dilution, you have added indefinite amount of water. So what is going to happen? Whatever the conductivity will be arising after adding indefinite amount of water, so that conductive will be because of its cation and the anion, the sum of its ionic mobility of cation and the n ions. So how I can write down this definition? See, the law states that the law states that the equivalent conductivity the equivalent conductivity of any electrolyte at infinite dilution, that is lambda this sorry lambda infinite dilution in this eq, equivalent conductivity at infinite dilution, is sum of equivalent ionic conductivity of cation and the anion, is the sum of equivalent ionic conductivity of the cation and anion of that electrolyte. Now if you write down in this equation, so it is like this: at infinite dilation the equivalent conductivity is equals to this, that is C cation, and this A is the anion. So this is the formula. Okay, it's Caldes law. So what is more important here is the why Caldes law is so important and where we are going to use it. So that's an application. This is very important for application for this MCQ point of view. The application of Caldes law. Now see, it is used to calculate the conductance of weak electrolyte. This is the first application, to calculate the conductance of weak electrolyte. Second, it is used to calculate the degree of dissociation. Now for strong electrolyte, the degree of dissociation is a 1. Okay. So to calculate the degree of dissociation, that is alpha. So alpha is equals to lambda EQ upon lambda at infinite dilution equivalent. So I can write down in the form of statement: equivalent conductance at a given concentration upon equivalent conductance at infinite dilution. Equivalent conductance at infinite dilution. Okay, so this is the second application. Apart from this, it is used for calculating the dissociation constant for weak electrolyte. You must have heard Oswald dilution law that is applicable for the weak electrolyte. So it is used to calculate dissociation constant for weak electrolyte. Now see, there's a formula. Ka is the dissociation constant. Ka is equals to alpha square C upon 1 minus alpha, where alpha is less than or equals to 5%. If the dissociation is happening less than or equal to 5%, then we neglect it. If it is more than 5%, then we consider it. Okay, so K can be equal to alpha square into C if alpha is equals to or less than 5% of dissociation. Okay, if you take it alpha as a 1, it means it is a strong electrolyte. So the whole, this, the denominator will become 0 if you have taken alpha as a 1. So this is getting not defined. So that's why this is not applicable for the strong electrolyte, because for the strong electrolyte the value of alpha is considered as a 1. Okay, now the fourth one that is very important, your application is the solubility and the solubility product of any sparingly soluble salt. Solubility, that is S. Solubility, and the solubility is also called as a concentration, you can consider, because whatever amount of solute will dissolve in the water, that is going to give its strength. And KSP, solubility product of any sparingly soluble salt. Any sparingly soluble salt. Okay. No, sparingly soluble salt means they are very, very less soluble. No, sparingly soluble salt means it's very less soluble. Okay. And for saturated solution, means further you cannot do any kind of dissolution. You cannot dissolve any further solute or the salt. That saturated solution of sparingly soluble salt can be considered as infinite diluted solution. Can be considered as infinite dilute solution. So the molar conductivity, that is lambda m, is the formula is like 1000 into K specific conductance upon molarity. Okay, and molarity is considered as a solubility also, as I told you, because whatever the concentration of solute is dissolved, that is its your solubility. Okay, so this was the fifth application, or I can call this, the first one was the, yeah, conductance of weak electrolyte, then degree of dissociation, and then relation between the Ka, and this was the yeah, fourth one, solubility and KSP. After that, we have how we can construct a cell. The cell is made up of two half cell, that is your anode and the cathode. Okay, so we'll try to understand construction of a cell. Construction of cell. As we know that your voltaic cell, galvanic cell, like Lenz's cell and all, so they have a two compartment. One is the anode and other is a cathode. Okay, so the cell is made up of what? It has a two half cell. It has two half cell, each having a beaker containing metal strip dipped into the aqueous salt solution. Having a beaker containing a metal strip, that is an electrode, metal strip that dips in its aqueous salt solution. Okay, I will give you the example. The metal strips are called as the electrode. Metal strips are called as electrode, and the two solutions are connected by a salt bridge because they are the two half cells. They are connected by the salt bridge. Two solutions are connected by salt bridge. Now, what is a salt bridge? That we'll see, because in the board exam they ask for 2 mark. Write a short note over the salt bridge. After that, oxidation is happening at the one compartment where the anode is present, and reduction is happening at another compartment where cathode electrode is present. So if I draw the diagram here, suppose I have a beaker on the left hand side that contains the ZnSO4 solution, and on the right hand side I have another beaker that contains the copper sulfate solution, and there is a copper electrode. So I will be just putting the electrode here. This is the electrode of zinc on the left side. On the right side I have an electrode of copper, and they are connected. This is your I can say bulb. You can imagine it will glow when the circuit is getting connected, and there is a battery also. Okay, so this is your zinc, Zn. This is your copper, and the solution is like ZnSO4, and this solution on the right hand side, this is the copper sulfate. Now this is not complete circuit at all. This is not a complete circuit. So when you connect here salt bridge is the inverted U-shaped glass tube. It is an inverted U-shaped glass tube that is filled with agar-agar gel, and there is a KCl or KNO3 electrolyte is placed inside the tube, and it is plugged with the cottons, and there is a gel present inside the tube. Okay, so now what happened when the circuit is on? The zinc loses electron and forms Zn plus 2, and this 2 electron. This 2 electron is getting traveled with the external circuit, that is a wire, and internally there is a transfer of an ion. So that Zn plus 2 gets combined with the Cl minus. That Cl minus is coming from the KCl, and it maintains the electrical neutrality. Okay, and the copper gets these 2 electron and gets converted into the Cu. So you can say here the zinc is getting oxidized at anode, and this is getting copper is getting under reduction, and getting reduction process. So this is about the construction of a cell. And salt bridge, as I told you, it is an inverted U-shaped glass tube filled with agar-agar gel or gelatin also, and it is placed inside the KCl solution or KNO3 solution. It is used to maintain the electrical neutrality. It avoids the liquid junction potential. So these are the few advantage of your salt bridge. Now the last concept about the lecture number 2, which we are going to learn, how to do the cell representation. How to do cell representation. Now see, you got a left hand side and you got a right hand side whenever you are drawing the cell. So on the right hand side, there is a reduction happening, and on the left hand side, there is an oxidation happening. Whatever the electrode is placed on the right hand side, you need to consider them to be undergoing reduction. Okay, and this is a double vertical line. This double vertical line means this is a salt bridge. This is the salt bridge. Now, if I want to write down the cell representation of the this equation which I had just this cell, if I want to write down the cell representation for this particular cell, so how it looks like, see, the oxidation is happening for the zinc, so zinc has to be in the left hand side, and zinc is in the form of what? It is in the form of solid. and zinc is in contact with its own ion, that is Zn plus 2, and that the physical state is the aqueous. So when you got a two different state, that is solid liquid or the solid gas, so they need to get separated by the single vertical line, and then there is a double vertical line. So I just need to place this double vertical line very close to this. So zinc solid single Zn plus 2, that is aqueous, double vertical line, that is a salt breach, and then you got a copper solid on the right hand side, and that copper solid is in the contact with the copper ion Cu plus 2, and that too aqueous. So this is the cell representation of the particular for this particular cell. So what is here important whenever you write on the physical state, that is two phases, that is state of matter is getting separated by the vertical line, single vertical line, and the salt bridge is getting represented by the double vertical line. So this is the only your representation, and right hand side is a reduction, left hand side is the oxidation. I hope everyone is getting this, whatever what I have explained in this particular lecture. So this was all about the lecture number 2. In the lecture number 3, I will explain the electrode potential and the types of your reference electrode. There's a primary and the secondary. So thank you for seeing this video lecture.